Thank you for the invitation to present at today's meeting. So I'm Calum Baugh from ECMWF. That's the European Centre for Medium Range Weather Forecasts. I'm based in Reading in the UK, but we're an international organisation. We have offices in Bonn, Germany, and Bologna in Italy. So I'm going to talk about flash flood forecasting at the pan-European scale within CEMS-Floods EFAS. So a bit of an acronym. CEMS is the Copernicus Emergency Management Service, and EFAS is the European Flood Awareness System. So I'll just give a quick overview of where within Copernicus this all sits. So Copernicus being an initiative of the European Union. So all of this is funded by the European Union. So Copernicus is their service for observing Earth, what's happening now, but also predicting future hazards. So there are these 6 core services that you can see along the bottom here. And where these activities about flash flood forecasting come into is the emergency service on the bottom right there, highlighted in the red box. So within that emergency service, there are actually many different components. We have a service about early warning of floods, which is highlighted in the red box there. But there's also early warning and monitoring of fires and droughts. We also have like on-demand rapid mapping. So after an event or whilst an event is ongoing, a European EU member state could activate satellites operated by Copernicus to go and observe the disaster, and then there can be a damage assessment from that. But my talk today will focus on the early warning for floods there in the red box. So within CEMS-Floods, we have on the bottom there the global flood monitoring, which is using Sentinel-1 to monitor ongoing flood events. But for predictions on the top here, highlighted in the red box, we have 2 forecasting systems. So EFAS, the European Flood Awareness System, and GLOFAS, the Global Flood Awareness System. The flash flood forecast products are only available in EFAS, so for Europe. So that's what I'm going to focus on today. And in terms of what organizations are doing this, I'm from ECMWF. I'm talking about Copernicus funded by the EU. So how does this all fit together? So CEMS-Floods, the project is set up in this way here. So at the very top, you've got the JRC, the Joint Research Centre of the European Commission there, what's called the entrusted entity. They are entrusted by the European Commission to run the overall CEMS-Flood project. And then there is a certain number of contractors for this project, of which ECMWF are one of them. So in this case, we are what's called the computational center, and that means we are responsible for running the models, so the hydrological models and others, to produce hydrological forecasts. And for that, we need input from meteorological observations and hydrological observations that you can see on the left. And then when we run our forecast chain, those products are disseminated via a web service, and notifications are issued to users by our dissemination centers there on the right-hand side, who are led by the Swedish, Slovak, and Dutch, so the Hydromet Agency and it's the Dutch Water Agency. So jumping straight into the flash flood products. So EFAS itself has many different hydrological forecasts of stream flow, but they're all produced by a hydrological model, which is called ListFlood. Now, they can be quite coarse in spatial resolution. So we actually have a separate suite of flash flood products, which can be higher resolution, higher temporal resolution, higher forecast frequency to try and capture these events, which are obviously very dynamic in nature. So the first grouping of products we have are called ERIC. I'll tell you what the acronym stands for in I think the next slide. Basically, these are a kind of medium range, in inverted commas, products that could give warning up to about 5 days ahead. So they are produced twice a day at 00 and 12 UTC. They're all across Europe, as you can sort of see in this area here where the triangles are shown. And they have a sort of spatial resolution of around about 1.4 kilometers. It's 1 arc minute, and a 6-hour time step. They're focused on riverine flash flood events. So they're not going to capture pluvial events in cities. They're really meant to sort of highlight the sort of smaller upstream tributaries where the upstream drainage area is less than 1,000 square kilometers. They're really meant to highlight those upstream tributaries where heavy rainfall could lead to a sort of sudden increase in surface runoff, basically. And from these products, we can issue notifications to partners. So these are EFAS partners. They are typically hydrometeorological agencies and civil protection agencies. who can sign up to receive these notifications. And the rule that we have to send out a notification is we have a maximum of 2-day lead time where there is a 30% or more exceedance probability of the 5-year return period. That's a static rule, but there's some work which I'll explain later to maybe allow users to tailor that. And the other set of products we have are what we call sort of nowcast experimental products. So they're based on radar nowcasts, and in some cases a blending with NWP data. And they highlight, so in the middle here, this is a product which uses radar data to highlight sort of small rivers, which could be at risk of flash flooding. And on the right here, there's some products which can highlight the areas at risk of pluvial floods. These, we call them experimental products. So they run once every hour, but they're not fully operational. So if the kind of computing system falls over during the night, it's only going to be picked up and fixed during working hours. So that's why we call it experimental. So just to talk about the first block of those, the ERIC product. So ERIC stands for Enhanced Runoff Index Based on Climatology. It was developed at the JRC back in 2015. And basically what it is it's an accumulation of model surface runoff on this, or it's actually a 1.5 kilometer channel network, and then comparing those against climatological thresholds. So the workflow here, if we start on the top left, we get numerical weather prediction forecasts of precipitation and temperature from the COSMOLEPS limited area model. That's a 20-member ensemble forecast produced by a consortium where I think they're headed up in Bologna. The forecasts are made twice a day. We have 6 hourly time steps. They go up to, well, actually 7 days, but we only use the data up to 5 days. And I have a 7-kilometer spatial resolution. We put that into the ListFloods hydrological model. And from that, we get forecasts of surface runoff. So that means we can include things like antecedent soil, wetness, snow melt, etc. And then we take that surface runoff and sort of instantaneously accumulate it on the channel network. And we look at accumulations which are much coarser in time in terms of 6, 12, and 24-hour time periods. And then we compare those accumulations against the mean annual maximum from a sort of 19-year climatology series from COSMOLEPS reforecasts. And where that mean annual maximum is exceeded, we sort of trigger the production of the flash flood warning products, which I'll go into detail for a case study on the next slide. So yeah, this more or less just restates what I've said there. The rivers that we produce this product for have an upstream drainage area between 25 square kilometers to 1,000 square kilometers. So this is an example of what the products look like for Storm Leonardo in Spain in February earlier this year. So this was one of a procession of storms that affected the Iberian Peninsula over the winter of 2026. It was just storm after storm, and there was several bouts of bad flooding across the peninsula. And in this particular case, Andalusia in southern Spain was particularly badly affected. So I'll just go through what we're looking at here. So firstly, this is a screen grab from the EFAS forecast web viewer. So the layers are available in this flash flood tab. And what we're viewing is the forecast at 12 UTC on the 2nd of February, so roughly about 2 days ahead. And firstly, these kind of like purple and red lines that you can see drawn on the map, this is what we call the affected area. So this is highlighting the rivers themselves where flash flooding may be possible. So these are the areas upstream of where these triangles are located. So purple highlights where there's a risk of exceeding the 20-year return period. This is all computed from the model climatology. This isn't based on like gauging station observations to derive those return periods thresholds. And the red is where there's a chance of exceeding the 5-year return period, but not the 20-year. Then a user can click on the reporting points. These are the inverted triangles where they can see some time series information. So it's a hydrograph, but it's not, because it's not discharge. On the y-axis is the sort of estimated return periods from this product. And you can see it going out for the next 5 days. And the yellow color is where you're between the 2 and 5-year return period. The red is between the 5 and the 20-year, and the purple is the 20-year and above return period. We top it out at 500 because obviously the fitting of the distribution goes a bit crazy. So in this particular case, you can see that around about 48 hours ahead, you've got you can see this the real peak coming from the rainfall as this sort of storm made landfall, if you like to use sort of tropical cyclone terminology. Um, and then the other thing you'll see there are sort of these blue triangles, and these are locations where our dissemination center have issued flash flood notifications to partners. So in this case, the Andalusian Environment Agency and I think it was the Guadiana and Guadalquivir basin authorities would have received, and the Spanish National Civil Protection Authority would have received notifications about flash flooding in this area 2 days ahead. So this is kind of like great for sort of larger storms where it's the NWP models have this ability to capture those systems, but particularly for convective events, the NWP models aren't very good at highlighting that risk. So this is where we have these radar-based products where we're using radar nowcasting to also calculate flash flood products. So this is just an animation for the same Leonardo event in Spain, but just in the hours before and during the sort of onset of the storm. So what you can see here is as the rain, which is shown in the sort of greens and blues in the background, as that progresses through the area, you can see sort of like red and purple and orange catchments being highlighted. And those are where we're predicting the risk of river flash flooding. So we produce these forecasts every hour. For the first 5 hours, they have 1 hour time step, and it's made by a blending of radar nowcast and NWP data that's actually coming from ECMWF IFS. And then for longer lead times, it's the data, the flash flood products only produced using the IFS numerical weather prediction. And there we just make some summaries between these lead time windows rather than showing the animated evolution of the storm. So how those products are created. So firstly, we have a blending of radar nowcast data. Those nowcasts are derived from radar observations, which come from EOTEC, which they're Opera products. So it's a composite of radar observations across Europe. You can see in the top left there. We use a nowcast method called SBMcast, which was produced by the Polytechnic University of Catalonia to make a nowcast. That's a 20-member ensemble. We then blend it with our 51-member NWP ensemble. We apply some bias correction relative to rain gauge observations and remove frozen precipitation. We then calculate the flash flood hazard in much the same way that we calculate the ERIC product that I described previously, but here we're only using precipitation rather than runoff because we can't run a hydrological model in time. And then again, we compare those accumulations versus climatology. One slight difference here is that the accumulation periods are shorter. So we have 1, 3, 6, 12, and 24 hours. But the accumulation period is in each grid cell is different depending on the time of concentration of the river. And then from that, we compute flash flood impacts. So we overlay the flash flood hazard, which you can see in the middle, with information about population and critical exposure, which goes on the top right here in an impact matrix. So you can have a high likelihood of flash flooding on the x-axis of this matrix. And if you have a highly populated area, you would then go in the top right sort of purple cell here. And we sort of summarize that over catchments, but also highlight the specific locations within the river network as well to sort of try and identify the most at-risk locations. So these products, they're in EFAS now, but we have a project called Inline where we're constantly trying to refine these radar-based products. So it's a project led by the Polytechnic University of Catalonia and also has these institutions here. So it's a 2-year project. So started in February last year and runs to February next year. And basically, we're trying to develop flash flood products for possible integration into EFAS. So some already are, and we're refining those, and others are new layers which we'd like to do. There's too many developments to talk about, but two that I'm particularly keen to raise. One is about users being able to define their own notifications. So what you can see here is a box that users can specify which products they're interested in, how frequently they'd like the notifications. They can say what area they're interested in, and also what levels. So they might only be interested in like red and purple. So that means they won't get notified for the sort of lighter orange shades. which is quite nice. Another thing we're allowing them to do is to upload their own exposure data. So we use pan-European estimates of population, but they might have much higher resolution, more accurate estimates of population. So they can upload that into a database, and then the products are recomputed using that. And the other thing that we're working on, hopefully this video works, is just to refine how we show the layers in EFAS. So at the moment, how we show the products in EFAS is a bit counterintuitive. They're all split into separate layers. But this is a video produced by my colleague who, instead of having like gridded products, we show river vector lines, which you can click on, and they're exploring the data here. So yeah, it will play through again. So they're zooming in eventually. Yeah, you can click through the timelines. It's very quick because it's a vector layer rather than trying to render a netcdf. And then you can see you have the river vector line here. So the purple is where there's higher impacts. You click on it, it comes with a pop-out window, which will have more information. So it would show you where, what the impact level is and what the sort of affected population is. So this is the final slide. One other activity that we do in line is we have a community of interest. We meet roughly about every 6 weeks, and we have users from these countries in blue, and they come from a range of different institutes like hydrometeorological agencies, civil protection agencies, and others. And basically what we do is we present the latest project developments, get their feedback, but they also present to us like the latest events that may have happened or a look back at an event that happened a while ago. And they look at the products that we're producing in this inline project and give us feedback, crucially, on how to improve them. We've had tons of interesting feedback, and it's good that they're brutally honest, because ultimately we want to make stuff that that is useful for them. So if you're interested to join, please send an email to this email address, and we can get you set up to access the project platform, and then join the next meeting, which will be in September. So thank you very much, and back to